For this final video on binary search trees, I want to talk a little bit about implementation details for the red-black tree data structure, in particular the insertion operation. As I've said in the past, it really doesn't make sense for me to spell out all of the gory details about how this is implemented. If you want to understand them in full detail, you should check out various demonstrations readily available on the web, or a comprehensive textbook, or an open source implementation. Red-black trees, you'll recall, satisfy 4 invariants, and the final 2 invariants in particular ensure that the red-black tree always has logarithmic height, and therefore all of the supported operations run in logarithmic time. The problem is we've got to pay the piper. Whenever we have an operation that modifies the data structure, it potentially destroys one or more of the invariants, and we have to then restore that invariant without doing too much work. Now, amongst all of the supported operations, there are only 2 that modify the data structure: insertion and deletion. So from 30,000 feet, the approach to implementing insert and delete is to just implement them as if it's a normal binary search tree, as if we didn't have to worry about these invariants. And then if an invariant is broken, we try to fix it with minimal work. And the 2 tools that we have at our disposal to trying to restore an invariant are, first of all, recoloring, flipping the color of nodes from red to black, and second of all, left and right rotations, as covered in the previous video. My plan is to discuss the insertion operation, not in full detail, but I'll tell you about all of the key ideas. Now, deletion, you got to remember that even in a regular binary search tree, deletion is not that trivial. And in a red-black tree, it's downright painful. So that I'm not going to discuss. I'll defer you to textbooks or online resources to learn more about deletion. So here's how insert is going to work. So suppose we have some new node with the key X, and we're inserting it into a red-black tree. So we first just forget about the invariants and we insert it as usual. And remember, that's easy. All we do is follow left and right child pointers until we fall off the end of the tree, until we get to a null pointer, and we install this new node with key X where we fell off the tree. That makes X a leaf in this binary search tree. Let's let Y denote X's parent after it gets inserted. Now, in a red-black tree, every node has a color. It's either red or black. So we have a decision to make. We just added this new node with key X, and we got to make it either red or black. And we're sort of between a rock and a hard place. Whichever color we make it, we have the potential of destroying one of the invariants. Specifically, suppose we color it red. Well, remember what the third invariant says. It says you cannot have 2 reds in a row. So if Y, X's new parent, is already red, then when we color X red, we have 2 reds in a row, and we've broken invariant number 3. On the other hand, if we color this new node X black, we've introduced a new black node to certain root null paths in this tree. And remember, the 4th invariant insists that all of the root null paths have exactly the same number of black nodes. So by adding a black node to some, but not all of the paths, we're in general going to destroy that invariant if we color X black. So what we're going to do is we're going to choose the lesser of 2 evils, and in this context, the lesser of 2 evils is to color X red. Again, we might destroy the 3rd invariant. We'll just deal with the consequences later. So why, you ask, is coloring X red and destroying the 3rd invariant the lesser of 2 evils? Well, intuitively, it's because this invariant violation is local. The flaw in our not quite red-black tree is small and manageable. It's just a single double red, and we know exactly where it is. It's X and Y. So there's sort of more hope in squashing it with minimal work. By contrast, if we colored X black, then we've violated this much more global type of property involving all of the root to null paths. And that's a much more intimidating violation to try to fix than just this local one of having a double red between X and its parent. Indeed, some of the time we'll just get lucky, and it will just so happen that X's parent Y is colored black. And then we're golden. This new node X that's colored red, it doesn't create a double red. There's no other violations of the other invariants, and so boom, we've got a new red-black tree and we can stop. So the tricky case then is when X's parent Y is also red. In this case, we do not have a red-black tree, we have a double red, and we have to do some more work to restore the 3rd invariant. So suppose y is red. What do we then know? Well, remember, before we inserted x, we had a red-black tree. All 4 of the invariants were satisfied. So therefore, y, by virtue of being red, it could not have been the root. It has to have a parent. Let's call that parent w. Moreover, by the third invariant, there was no double red in this tree before we inserted x. So by virtue of y being red, its parent w must have been black. So now the insertion operation branches into 2 different cases, and it depends on the color, on the status of W's other child. So in the first case, we're going to assume that W's other child, that is not Y, but the other child of W, exists and is colored red. In the second case, we're going to treat when W either doesn't have a second child, Y is its only child, or when its other child is colored black. So let's recap where things stand. So we just inserted this new node, and it has the key x. And our algorithm colored this node red. So x is definitely red. Now, if its parent y was black, we already halted. So we've already dealt with that case. So now we're assuming that y, x's parent, is also red. That's what's interesting. Now, by virtue of y being red, we know that y's parent, that is x's grandparent w, has to be colored black. And for case 2 of insertion, we are assuming that W has a second child, call it Z, and that Z is colored red. So how are we going to quash this double red problem? We have 2 tools at our disposal. One is to recolor nodes. The second is to do rotations. So for case 1, we're only going to actually have to do recoloring. We're not even going to have to bust out our rotations. In particular, what we're going to do is we're going to recolor Z and Y black, and we're going to recolor W red. So in some sense, we take the reds that are at Z and Y and we consolidate them at W. The important property of this recoloring is that it does not break the 4th invariant. Remember, the 4th invariant says that no matter which path you take from the root to a null pointer, you see exactly the same number of black nodes. So why is that invariant still true after this recoloring? Well, for any path from a root to a null pointer which doesn't go through the vertex W, it's irrelevant. None of these nodes are on that path, so the number of black nodes is exactly the same. So think about a path which does go through W. Well, if it goes through W, to get to a null pointer, it has to go through exactly one of Z or Y. So before we did the recoloring, this path picked up a black node via W, and it did not pick up a black node via Z or Y. Both of those were red. Now, any such path does not pick up a black node at W, that's now red, but it does pick up exactly one black node, either Z or Y. So for every single path in the tree, the number of black nodes it contains is exactly the same before or after this recoloring. Therefore, since the 4th invariant held previously, it also holds after this recoloring. The other great thing is that it seems like we've made progress on restoring the 3rd invariant, the property that we don't want any double reds at all in the entire tree. Remember, before we did this recoloring, we only had a single double red. It involved X and Y. We just recolored Y from red to black. So certainly we no longer have a double red involving X and Y, and that was the only one in the tree. So are we done? Do we now have a bona fide red-black tree? Well, the answer depends, and it depends on the color of W's parent. So remember, W just got recolored from black to red. So there's now a possibility that W, being this new red node, participates in some new double red violation. Now, W's children, Z and Y, are black, so those certainly can't be double reds. But W also has some parent, and if W's parent is red, then we get a double red involving W and its parent. Of course, if W's parent was black, then we're good to go. We don't get a double red by recoloring W red, so we have no double reds in the tree, and we can just stop. Summarizing, this recoloring preserves the 4th invariant, and either it restores the 3rd invariant, or if it fails to restore the 3rd invariant, at least it propagates the double red violation upward into the tree closer to the root. We're perfectly happy with the progress represented by propagating the double red upward. Why? Well, before we inserted this new object x, we had a red-black tree, and we know red-black trees have logarithmic height. So the number of times that you can propagate this double red upward is bounded above by the height of the tree, which is only logarithmic. So we can only visit case 1 a logarithmic number of times before this double root is propagated all the way to the top of the tree, all the way to the root. So we're not quite done. The one final detail is what happens when this recoloring procedure actually recolors the root. So you could, for example, look at this green picture on the right of this slide and ask, well, what if W is actually the root of this red-black tree and we just recolored it red? Now notice in that situation where we're dealing with the root of the tree, we're not going to have a double red problem. So invariant 3 is indeed restored when we get to the top of the tree. But we have a violation of invariant number 2, which states that the root must always be black. Well, if we find ourselves in this situation, there's actually a super simple fix, which is this red root, we just recolor it black. Now, clearly that's not going to introduce any new double reds. The worry is that instead it breaks invariant 4. But the special property of the root vertex is that it lies exactly once on every root null path. So if we flip the color of the root from red to black, it increases the number of black nodes on every single root null path by exactly 1. So if they all had the same number of black nodes before, they all have the same number of black nodes now after the recoloring. That completes case 1 of how insertion works. Let's move on to case 2. So case 2 gets triggered when we have a double red, and the deeper node of this double red pair, call it X, its uncle, that is if it has grandparent W, parent Y, and W's other child other than Y, either doesn't exist, or if it exists, it's colored black. That is case 2. I want to emphasize you might find yourself in case 2 right away when you insert this new object X. It might be that immediately it has some uncle which is colored X, or it might be that you've already visited case 1 a bunch of times, propagating this double red up the tree, and now at some point the deeper red node X has a black uncle. Either way, as soon as that happens, you trigger case 2. Well, it turns out case 2 is great in the sense that with merely constant work, you can restore invariant number 3, you can get rid of the double red without breaking any of the other invariants. You do have to put to use both of the tools we have available in general, both recolorings and rotations, left and right rotations, as we discussed in the previous video. But if you do just a constant number of each, recolorings and rotations, you can get all 4 of the invariants simultaneously. There are unfortunately a couple of subcases depending on exactly the relationships between X, Y, Z, and W. For that reason, I'm not going to spell out all the details here. Check out a textbook if you're interested, or even better, work it out for yourself. Now that I've told you that 2 to 3 rotations plus some recolorings is always sufficient in case 2 to restore all of the invariants, follow your nose and figure out how it can be done. So let's summarize everything that we've said about how insertion works in a red-black tree. So you have your new node with key X, you insert it as usual, so you make it a leaf, you tentatively color it red. If its parent is black, you're done. You have a red-black tree and you can stop. In general, the interesting case is this new node X's parent is red. That gives you a double red, a violation of invariant 3. Now what happens is you visit this case 1, propagating this double red upward in the tree. This upward propagation process can terminate in one of 3 ways. First of all, you might get lucky, and at some point the double red doesn't propagate. You do the recoloring in case 1, and it just so happens you don't get a new double red. At that point, you have a red-black tree, and you can stop. The second thing that can happen is the double red propagation can make it all the way to the root of the tree. Then you can just recolor the root black, and you can stop with all of the invariants satisfied. Alternatively, at some point when you're doing this upward propagation, you might find yourself in case 2, as discussed on this slide, where the lower red node in your double red pair X has a black or non-existent uncle Z. In that case, with constant time, you can restore all of the 4 invariants. So the work done overall is dominated by the number of double red propagations you might have to do. That's bounded by the height of this tree, and that's bounded by big O of log n. So in all of the cases, you restore all 4 invariants. You do only a logarithmic amount of work, so that gives you a logarithmic insertion operation 4 red black trees as promised.